Okay, thank you very much, and thank you for the organizers for inviting me here. It's very nice to be back in Brazil and celebrate the 25th anniversary of the ADS CFT correspondence. I will tell you about some work I've been doing in recent years about surface operators and their holographic descriptions in terms of M2-branes. I listed here a lot of papers on the topic. I will not cover them in full detail, luckily. Where did the red dot go? Red dot is dead. And most of it is work in collaboration with Maxime Trepanier, who was my PhD student, but since then has become a postdoc and has found better things to work on, I guess. And he's still a few projects with me, but now handing over to a new PhD student. We don't have public defenses when you finish your PhD in England. So we can view this as his public defense. If I do a bad job, maybe we revoke his PhD. I leave it to your decision. So the motivation for this research project was to try to see what we can do with surface operator that has worked so well with Wilson loops as an ideal laboratory for the ADS CFT correspondence. And some of the things that works for Wilson loops will not work for surface operators. Other will work just as well, and try to explore it and see how far we go. And in the talk today, I will focus a little bit more on the holographic side of things, but there are a few other methods that we can use, and we can learn about surface operators, about the 2,0 theory. So these surface operators will mostly be in the 2,0 theory, and more generally non-perturbative methods in CFTs, because this theory does not have a perturbative description. So as an outline of the talk, I will tell you about what was done in the very first years of the ADS CFT correspondence. And then I will tell you about what we did more recently. In a way, there was no reason that this could not have been done 20 years ago. And I will, there is a bit of a sociological reason why it wasn't done. But I think we learned a lot of stuff. Of course, things go much faster now with a lot of prior knowledge, so we could do quite a lot. So, back in the old days, if we wanted to study surface operators in the 2,0 theory using the ADS CFT correspondence, the only examples that were studied in detail were the plane, the infinite plane. Here is just a part of it. And then there is a holographic description of it in terms of a M2-brane in ADS 7 cross S4, whose world volume is ADS 3. Very similarly to it, you can take a sphere. Sphere is a conformal transformation of a plane, and it will also be described by an M2-brane taken at ADS 3 geometry. And already in the paper where Juan calculated the quark anti-quark potential in n equals 4 super n mils at strong coupling, he also calculated the potential between a plane and an antiplane and found some answer from strong coupling. There was a lot of progress in deriving the quark anti-quark potential from integrability. There hasn't been any progress in calculating this number in any other way. So this is sort of part of what we're hoping to fix to some extent, but we're still not there yet. Now, surface operators suffer from anomalies, and the main question you ask when you're going to be faced with when studying surface operators as opposed to line operators are, what are these anomalies? So when you look at a local operator in a conformal field theory, it can have a classical dimension, it can have an anomalous dimension, and that will manifest as some logarithmic divergences in a Feynman diagram calculations, and it will also manifest that when you rescale things, so when you look at a two-point function, it scales with the distance non-trivially. So it is conformal, but it's not conformally invariant, it's conformally covariant. The dependence on the distance does show up. And then we assign a dimension, classical or anomalous, to local operators. And the same is true for surface operators, except that they have 3 or 4 different anomaly coefficients, depends on how you count them. And in the basis that I work in, these are A1, A2, B, and C. And these are local quantities on the surface. Sorry, they are integrated against local quantities on the surface, which is the Ricci scalar of the surface. This is some quantity including the mean curvature and the pullback of the Schouten tensor. This is the pullback of the Weil tensor from the bulk, which will vanish if we're working on R6, if the theory is on R6. And this is something related to the breaking of R symmetry by the defect. So we can include we can orient every point of the surface in a different direction in R space, and this would be the square of the derivative of that. So here they are all defined. And the analog of finding the anomalous dimension is finding these numbers A1, A2, B, and C. And under conformal transformation, these factors will transform, these geometric factors transform appropriately, and you will see how the expectation value of your surface operator will transform. And this log, I'm writing here this log epsilon explicitly. It's the same as the kind of log that will appear in a perturbative calculation of a local operator. So this is the most salient feature of a surface operator, and given a type of surface operator, irrespective of its geometry, you need to calculate these 4 numbers. And these 4 numbers were calculated holographically by Graham and Witten very early on. And this is a beautiful calculation. And what it involves is taking a surface of arbitrary shape at the boundary of ADS, and then to calculate this, the expectation value of this observable, you need to find the minimal surface, the minimal M2-brane inside ADS7, or ADS7 times S4, that ends on the boundary. Now, generally, this is a very, very hard problem. I showed you 3 slides ago where were the only examples that we could do. But what Graham and Witten showed is that they can solve for this minimal surface close to the boundary, and that is enough to determine these numbers that are the things that specify the main property of the surface operator. Now, this seems very surprising that you can find this without the full solution. On the other hand, it's also very obvious because these are local quantities that should be integrated along the surface. You shouldn't really know the full structure of the solution to find them. So this is what was known back then. Then it took many, many years and the work of many people, and only recently the corrections to this beyond the leading large N results were found. And A1, which was here 0, gets a finite and a 1 over n correction. A2 gets also a finite and a 1 over n correction, and that is supposed to be all. C is equal to minus A2, B is equal to 0, and that is it. These were not found, these were found by these subleading in n terms were found in indirect methods, but they should be correct. And what I quote here is for the analog of the fundamental Wilson loop. So it's a surface operator in the fundamental representation in a way. There are expressions also for other surface operators. So for example, if we take the case of the sphere and we plug this in, so for the sphere, we have a scalar curvature. In this basis that I work, there is also a contribution from this kind of extrinsic curvature term. And you get some combination of A1 and A2, and that gives you this answer. And here I removed this epsilon. So in the same way that for a 2-point function of a local operator, you just write it as 1 over the distance to some power. This is the behavior for S2. And this is the answer. And this is where the field has been for a very, very long time. And then the question is, what can we do beyond this? This sort of answers the question. So Graham and Witten answered it at leading order in n. All these people answered it to the subleading order. And what else then can we say? Between A1. No, at large n, it's 0. These are, so this is the order n terms. It's 0 at order n. It's 0 times n, yes. It's 0 times, what, the A1 up here, it's 0 times n plus finite plus 1 over n. And they didn't calculate finite or 1 over n. This is the finite and 1 over n. So, the analog of this question is this answered to some extent for the simplest observable, for the simplest kind of surface operators that we know in the theory, this resolved the question of what are the anomalous dimensions. If we think about local operators, this is, to some extent, we know that very well from integrability. But then, okay, if we know the spectrum, that doesn't fully solve the theory. What else can we do? With local operators, we would want to calculate 3-point functions, for example. So are there other calculations that we can do with surface operators that go beyond the anomalies? And this is not very easy. We're used to it with local operators. If a local operator has anomalous dimensions, then the 3-point functions requires some effort to remove the anomalies and get a nice finite quantity. So this is the kind of things we were doing. But first, we decided to look for special classes of operators. And so these are operators that preserve a finite number of supercharges. And so out of the 32 supercharges of the theory, we try to find surfaces with special geometries that will preserve a finite fraction of them. And the plane preserves 16 supercharges. If you take an arbitrary shape, it will preserve none. But if you're clever and you choose a surface that is sort of made out of different planes, at every point you have a tangent plane, and these tangent planes preserve the same supersymmetries, you can find an object that has global supersymmetries. And we didn't do a full classification, maybe this is the full classification, but this was what we found by trial and error. We found 4 examples of conditions to get objects that are supersymmetric. I should note that it's very important to change also this analog of the scalar coupling, how the surface moves inside S4 to get this. So we have type R, where is it? Type R, type C, type H, type S, and I will describe them in a little bit of detail. And some of them are in all of R6. Some of them have all kinds of restrictions to be generic surfaces inside some submanifold. So type R, these are extended along a straight line in R6 and an arbitrary curve in the transverse 5 dimensions. And the condition is that the scalar coupling that I call here Ni is related to this curve in these 5 other directions. If I restrict this curve to be just a straight line, I get back the plane. If I restrict this curve to a 2-plane, I can make a cusp in that plane, and then the cusp times a line is what we call a crease. I will get back to it later. So there is a particular crease that is 1/4 BPS. And if you are familiar with BPS Wilson loops in n equals 4 super Young-Mills, these are uplifts of what are known as the Rimbaud Wilson loops that are supersymmetric in 4 dimensions. A nice feature here is that while the 4-dimensional observable has 0 expectation value, these have a finite quantity that we can calculate, a finite expectation value per unit length. And I will tell you what it is equal to at strong coupling, in the holographically in a little bit. Yeah, so all of those are invariant under Poincaré supersymmetries. Some of them also under superconformal symmetries, like the plane or the crease. Of all these classes, only type S here at the end does not preserve any Poincaré supersymmetries, if I remember correctly. Only combinations of Poincaré plus. So this is the analog of type S is somehow the closest analog of DGRT Wilson loops, if you wish. But type H is also somehow related to it. So it's yeah. But it's only linear combinations of Q plus S's. Type C. Now, if I view R6 as a C3, if I take a holomorphic curve in that and a constant scalar that is automatically supersymmetric, so this is the easiest thing to do. Oh, I didn't mention if I calculate these geometric quantities R, H, W, which in our case is 0 because I'm in R6. And this, I use the constraint that A2 is equal to minus C, and I calculate these quantities for type R, I will get 0. So there is no anomaly here. So I call them anomalous surfaces. Anomalous rather than anomalous. Sorry. And that's why they have sort of a finite expectation value. Type C are also anomalous. Sorry, type C are not anomalous. This is the anomaly. They're anomalous. And the anomaly depends on the Euler character of the surface. Type H is is a very intricate construction. So you take a arbitrary surface inside an R4. Your R4 is inside R6, and then you choose your n in terms of the two tangent vectors to the surface and the 't Hooft symbol. So there is some chirality involved here, and they preserve generally a single supercharge. And if you restrict it to be inside R3 instead of R4, you preserve two supercharges. And this is, if you're familiar with low-dimensional geometry, there is the Gauss map from a surface into, in this case of R4, it will be S2 times S2. This chiral projection is to a single S2. So these live on S2, of course, and the anomaly is related to the degree of the Gauss map, how many times you wrap this S2. The last example is type S, and I won't say a lot about it. The sphere is included in type S, and now you restrict to any surface inside a fixed S3. So in particular, you can take an S2. And then n is given in terms of the two tangent vectors and the position, the vector position. And it will play a role a little bit later, because we can, in the same way that you can conformally transform the plane to be a sphere, you can transform two intersecting planes, which is what I call the crease, to be two hemispheres inside S3. So I will look at that case later. And the anomaly is related to the Euler character of the surface, and then it also is related to the volume of the surface, which you will all complain about. That is not a conformal quantity, but here I already fixed the radius of this S3 to be 1, so it's the volume in units of radius of this S3. So again, if you want these to be anomalous, you can play around with these parameters and get it to be exactly 0, but that would be some kind of fine-tuning. We haven't been able to do anything particularly interesting with that. All of them have a nice description in M theory, the holographic description, because if the surface operator is supersymmetric, the M2-brane that describes it will also be supersymmetric, and in particular, it will satisfy some kind of projector equation. So here, epsilon is some killing spinor of ADS 7 times S4, and it will satisfy this equation. And using this epsilon, you can construct a 3 form. And this 3 form is somehow related to some G2 structure sometimes. And the surfaces satisfy this first very ugly differential equation, but it's simpler than the equations of motion. And the surfaces are calibrated if phi is closed, so the action is equal to the integral of phi, which is much easier than calculating the minimal surface and its area. So capital G is the bulk metric, little g is the induced metric, epsilon is the epsilon tensor, world volume epsilon tensor. Yes, still supersymmetry. Now, in the particular examples, these are the 3 forms that we find. And there is also one for type S, which is more complicated. In these 3 examples, the form is exact. So you can so you can do this integral, and you can reduce it to the boundary. And if you don't have an anomaly, if it is an anomaly, Graham and Witten already told you what that is. But if there is no anomaly, the finite term is this. It's just the square of the mean curvature. In the case of these type R ones, this would be just the curvature of square of the curvature of the line. But for all other cases, it's the same kind of quantity. So here we find if you don't have, if the anomalies cancel, if you have a finite observable, in these cases we can find what it is at leading order at large n. We don't. This is just from a classical M2-branes. We don't know subleading orders in n. One especially nice class is within type H. Some of them were anomalous. It's the anomaly. That's right. You need to find a prescription to remove the divergences. I will discuss that, but so let me say it this way. In the analog of local operators, if operators are protected, and this Kostya mentioned this morning, the coefficient on top of the two-point function is meaningful. If the operators have anomalies, the normalization of the operator is scheme dependent. The finite piece here is the analog of this scheme-dependent calculation. I will talk later about how I find scheme-independent finite quantities for surfaces that have these anomalies. So inside R4, I can take surfaces that are, so I'm looking at two surfaces inside R4, and I can take them to be Lagrangian, meaning that the pullback of the of this two form on the surface vanishes. This means that the image of the Gauss map is just inside an S1 instead of an S2. In particular, the degree is 0. And now I have both the chiral and this satisfy both the chiral and anti-chiral conditions. So I have two phis, two three forms, and that allows me to construct a complex three form in the geometry. And actually, this has a structure similar to a special Kähler manifold, and the M2-brane is a special Lagrangian manifold inside some 6-dimensional space inside ADS7 cross S4. So this is another structure that arises in holography that allows to find some other examples, but otherwise it's just a nice structure that we find. So to summarize, we have all kinds of examples, all kinds of supercharges that they preserve, all kinds of subclasses like the Lagrangian ones and so on. And furthermore, all kinds of other examples. Some of them were discussed previously, some of them not. And then we want to play with them and do some explicit calculations. So going back to the anomalous surfaces, I said type R are anomalous, Lagrangian surfaces are anomalous, and other fine-tuned examples. And so the simplest case is, well, the simplest case is type R. I actually already told you what the finite answer is in that case. But the simplest case of type H, which is Lagrangian, is just taking a torus a flat torus inside R4. Where is this? So I wrote here the coordinates. I coordinatize the torus. And if you follow the rules for what n should be, this is the answer that you get, and it preserves 4 supercharges. And then you can find what the answer is using the tricks that I told you, because we have a calibration form that is exact. But we can also find in this example the exact solution in an M theory, which is a filled torus, so it's a donut. Here, I don't expect you to follow it in real time, but this is the particular solution where you have 2 cycles and the smaller cycle shrinks. And then if you calculate the action, you find a term which is proportional to the area of the torus. This is divergent. Y here is the coordinate in ADS that goes to infinity. So this you renormalize away, and you find a finite quantity which is conformally invariant, depends just on the radius of the 2 cycles of the torus. And then you can take the limit of R1, say, to infinity, and you get a cylinder. This cylinder would be of type R. And you take the limit on this expression, and you find what I write here. And this is the same answer that we find from this prescription that I told you for type R. This would you would also get it from integrating this form that I had before. Now, for general end, the natural guess would be that you get an expression like this. And then the question would be, what is S0 and S1 beyond the leading large n limit? And unfortunately, I don't have an answer to that. We have another example that we studied. And now I should emphasize that in this case, I'm not only looking at the BPS example. So these are surfaces that can be BPS or can be non-BPS. And here, the analog for Wilson loops would be a cusped Wilson loop. But I take these 2 half planes and I glue them at an arbitrary angle to phi. There is the scalar coupling thing that I keep fixed on this and fixed on that, but at different. So that would give me another angle theta. If phi is equal to theta, these preserve some supercharges, 8 supercharges. If they are not equal, it doesn't preserve any supersymmetry, but it preserves this bosonic symmetry. And if I look at the planes, these don't seem to have an anomaly, but they're a little bit hard to deal with. So I compactify it with a conformal transformation to this picture where I have 2 hemispheres meeting at an angle. It's very hard to picture that because this is inside S3. But it's the analog of 2 hemicircles meeting at an angle like this. It's a 1-dimensional up analog of that. And there is also a picture of this in terms of a conformal transformation of R6 to ADS2 times S4. But let me work with this picture of the spheres. And now, for what Kostas was asking, I take the ratio of 2 of these kinds of examples. One is the round sphere. The other one is 2 hemispheres at arbitrary angle. This is a well-defined finite observable because these 2 things have the same divergences. So now I have a well-defined prescription, and I can calculate it. And we calculated it in the abelian theory, and the answer is log of cosine phi, the angle, plus some function of phi and theta. And this is the exact answer in the abelian theory. And then we calculated it holographically. It's a bit subtle, but we did the calculation. And we find the answer, which is, and expand, it's given in terms of, indirectly in terms of some elliptic integrals and so on. But then we expanded it, and for small phi, it starts, sorry, for small phi minus theta, that starts at cosine phi plus theta minus phi minus theta times tan phi. And then if you expand this guy in the same limit, you find that you get the same kind of quantity. So you have this universal behavior for the n equals 1 theory and for the large n theory. And we were able to prove, I'm not going to go over the proof here, using defect CFT techniques, that the dependence of this function, this effective potential, at theta close to phi, whatever it is, it's whatever it is at phi, plus the derivative of that with respect to phi, and that is, of course, that is consistent with the derivative, tan being the derivative of log of cos. And then if you look at these two examples at the value of u, it is also, in both of cases, it's log cosine phi. This is something we still don't have a proof for. So I expect this to be, that there should be some way to calculate it, but we haven't found it. And we also noticed that the coefficient in these two cases is equal to the anomaly coefficient C. Of course, it's just 1 in n or something like that, so it's a very natural number, but it does match. So there is here an open question, and something that in principle could be an exact calculation to do in this theory. So to conclude, let me show you the analogies between Wilson loops and surface operators. Apologies to those who are not experts on Wilson loops in n equals 4 super Young Mills. They won't know what the left-hand side is, but Kostya this morning sort of showed something similar to this. So the circular Wilson loop has an exact expectation value that we know how to calculate. If you uplift the cylinder, a circle to one dimension higher, if you want to make it into a surface operator, the most symmetric things could be a sphere or a cylinder. The sphere is anomalous with this scaling dependence, and that is known. The cylinder is finite per unit length t, and it's given by this number at leading order at large n. We don't know the subleading corrections, but again, this is somehow the most natural, simplest observable. It should have a nice expression. I don't know how to calculate it. This example as a Wilson loop with this shape of two hemicircles is also known exactly. It's just taken by this expression that we have here, and we renormalize lambda by the angle between these two half circles. And the analog of it is these two hemispheres meeting at an angle. And here we have this guess for what this dependence is. It's just this function here, but we haven't proven it. And then if you expand near it, this is what is known as the Bremsstrahlung function, or the generalized Bremsstrahlung function for cusp Wilson loop. And we have the analog of that for the near BPS two hemispheres. And here the question mark is just whether this is that function, but as I told you, we could prove that it is the derivative of that function, whatever it is. So this is the slide with the conclusions. I think we made some progress once we understood that what Graham and Witten were doing was solving for the anomalies, and then we need to do what you would do normally with local operators or with a bulk. Once you have the anomalies, how you get beyond them to find finite quantities. And we define all kinds of finite quantities, and we were able to calculate many of them. But many questions remain. Thank you.
Yeah, thanks for your very nice talk, Nadav. So, questions?
So the 2,0 theory on S5 times S1 should have a relation to maximal Young-Mills on S5, where you can imagine computing Wilson lines in the 5D theory with SUSY localization. Can you use those Wilson line results to learn something about what you talked about?
So I did include this in my talk. It is that point here. So the answer is that the uplift of those would be in R6. These would be cones because you're doing some kind of radial quantization, and so yes, you can get answers for cones from 5-dimensional super Young-Mills, and these people did it.
More questions?
To go back to my previous question, have you worked out covariant counter terms to remove the infinities?
In M theory or in the field theory, or so? No, so we haven't.
Because that will probably automatically give the relation you give. Like, for instance, in normal, the 2-point function of the energy momentum tensor, the coefficient is the same as the anomaly coefficient. That comes automatically once you have the counter terms.
Yeah.
So I think it should have the same origin.
Yeah, I assume that can be done. Yeah, we haven't done that.
More questions?
I have a similar question to the other one, whether reducing to n equal to 4 super Young-Mills you get any mileage or anything interesting.
I haven't succeeded in using that.
More? So can you just describe where you are going from here? I mean, is there something that you still need to complete in this program? I mean, are there next steps that you can do?
Yes, so I hid it in the. So I have some projects in progress. So so one question that I want to do is to derive some of these results directly from surface operators. They were calculated very indirectly, so I want to do it more directly by studying the spectrum of fluctuations of M2-branes, the asymptotic spectrum of fluctuations. So that is one thing, and the other thing is continue to try to apply tools there, find other examples, see how we can extract quantities and find quantities that are not renormalized, or where we can apply some form of some analog of localization, find all n results. Okay. It's a bit hard, but with these connections to 5D or possibly 4D and other tricks, yeah, that's where I'm hoping to go.
Yeah, thank you very much. All right, so thank you very much, Nadav.